Hello students, in our second lecture on semiconductor electronics, today we are taking diodes. Diode is an electronic component which is made by P and N region developed on a same block of the semiconductor. Normally, in making a diode, we take a small portion of highly pure silicon chip, a portion which is of the size of nearly a few micrometer. To this block, we initially dope the impurities of 13th group in such a way that the whole block becomes P region, something of this type. This entire region is made P-type by putting the impurities of 13th group. Then the upper portion is coated and the coated region is opened from a small portion through which impurities of the 15th group are doped inside, so that this region becomes N region. Then we do the electrical connection by taking two wires from it, and then it is sealed by a protective material so that it is not damaged from any changes from outside. In order to represent this diode in a simple manner, we have its schematic diagram where we show these two regions P and N, taking one portion as P type and N portion as the other side. The diagram is only giving you information that we have two regions here. Most of the study we will do by taking this diagram, is the simplest diagram. The symbol which we use to represent a diode is this one. This region is P type and this region is N type. This arrowhead actually is representing the current which can pass through a diode. We will see during the discussion that how the current passes through a diode in one direction. Before we go to the working of a diode, I would like to explain to you that how P and N regions are there and what are their energy diagrams. In the last lecture, we discussed that extrinsic semiconductor are the materials which are doped with impurities of 13th group for P region and 15th group for N region. They have band diagram, that is the energy diagram, where we are showing only the valence band and the conduction band. When the region is purely the semiconductor, or you can say is intrinsic semiconductor, the energy diagram is something like this. This is the valence band and this is the conduction band. As I told you, there is a gap between the two. The uppermost of the valence band and the lowermost of the conduction band, and we call this as the energy diagram or energy gap. This energy gap is of the order of 1 electron volt for a semiconductor. What happens when this semiconductor is doped with impurities of 13th group? When it is doped with 13th group impurities, it is called p-type semiconductor. We have valence band and conduction band of the base material. But along with this, when we dope impurities, these impurities also have their energy level. And this energy level lies very close to the valence band. This gap is very small, is of the order of 0.01 electron volt. It is very small. This is known as the acceptor level. The advantage we are getting is, for pure semiconductor, electron has to jump from valence band to the conduction band in order to participate in the electrical conduction, whereas in p-type semiconductor, electron has to jump only to the acceptor level, which means that the energy requirement is very small. Obviously, this is an easy way of electrical conduction. Therefore, p-type semiconductors, they have better conductivity as compared to the intrinsic semiconductor. What happens when it's on the N side? Again we have the similar energy level, that is the valence band and conduction band of the base material. But for N-type semiconductor, we get additional energy level very close to the conduction band. Once again, this gap is not very large. This gap is of the order of 0.01 electron volt, and we call this as the donor level. The donor level provides the energy level from where the electrons will jump to the conduction band instead of coming from the valence band. Since this gap is small, so electrons find this easy to go to the conduction band. Hence, again, conductivity of the N-type is better than the conductivity of intrinsic semiconductor. Keeping these things in mind, let's now understand what happens when PN junction is made. Initially, we are not taking any voltage given to the PN junction. When this junction is made, certain changes occur in diode. Let's understand that first of all. In a freshly made PN junction diode, we have a junction which is between the P-type and N-type. If I show it on the schematic diagram, as I told you that we are not taking the actual three-dimensional geometry. For simplicity, we are doing it with a schematic diagram where we are showing a PN junction as a slab. One portion is P-type and other portion is N-type. This is P region and this is N region. And this boundary is called junction. That's why sometimes it is called the junction diode. Since it is a single junction, there is only one junction which we have between the diode. Let's see in detail what is happening here. I told you in the previous lecture, in P region we have number density of holes more than the number density of free electrons, and in N region we have just the reverse of it. The number density of holes is less than the number density of free electrons. And at the junction, this difference creates a process called diffusion process. Let's understand this in detail. What happens? I'm making only this portion. In N region, we have more free electrons available as compared to the P region. These are called the majority carriers here. And obviously these electrons in the P region are called minority carriers. Diffusion is a process in which the entities may be atom, molecules or ions, or even the electron in our case, they move from high density region to the low density region. This diffusion of electrons from N region to P region starts the moment we make this junction. When the electron reaches in the P region, where the hole concentration is more, these electrons are absorbed in the hole, and hence we get electrons trapped in the hole region. Since they are coming from a region, electron is coming from that region, leaving behind the equal amount of the positive charge, and this process develops a current. We call it as a diffusion current ID, which is from the P region to N region. Please try to understand this, that as the electrons are coming here, the corresponding current is in the opposite direction. This process develops an electric field in the direction from N region to the P region. Now this electric field becomes strong and strong as the diffusion process goes on. Now this electric field starts another process, and that is the drift of the electrons from P region to N region, because electrons always move in the direction opposite to the electric field. And this drift current, which is due to the flow of electrons from P region to N region, develops a current. We call this current as the drift current. Since charge carriers are drifted by the electric field, notice one thing, that the diffusion current and the drift current, they are opposite in direction. Whole process starts with the diffusion current initially. As it develops, the drift current also starts increasing. And a stage comes when there is an equilibrium between the two. By that time, this region acquires some negative charge, and this region of N type acquires some positive charge. Once the equilibrium is made, one can say that there is a region where we have bound negative charge on P side and bound positive charge on the N side. This region is known as a depletion layer. The word depletion comes because these charge carriers cannot participate in the conduction process as they are bound. So this region is known as depletion layer. For most of the diodes, this is of the order of a micrometer. It is not and then the process stops. Obviously, on this side the negative charge decreases the potential, and on this side, that is on the N side, the potential is high. If anybody tries to give the potential, we have the potential on this axis. Due to this negative charge it is lower, and due to this positive charge it is higher on N side, and this difference is known as the barrier potential. Normally represented as VB. It is only a fraction of a volt, but plays a great role in the working of the diode. Now this is the story when there is no external electric field provided. Interestingly, one cannot measure directly this voltage using a voltmeter. If you connect a voltmeter across a PN junction, you are not going to get the measurement of this barrier potential directly. As these charges are bound charges, they won't leave to produce any current externally so that you can measure it with the help of any voltmeter or multimeter. There are indirect methods of measurement of this barrier potential. Now let's see, when this diode is connected to the external electric field, what happens? When you apply the electric field to a diode, there are two ways in which you can apply the electric field. We call the arrangement of the potential as the biasing of the diode. Biasing means, there is a term known as biasing, which is of two types as I told you. One is called the forward biasing and other is called the reverse biasing. In forward biasing, we have a diode connected in such a way that the P region is connected to the higher potential and N region is connected to the lower potential. In the reverse biasing, it is just the reverse of it. That means the P region is connected to the lower potential or negative terminal, and the N region is connected to the higher potential. In this case, the electric field is from P to E. This is the external electric field. And in this case, the electric field which you apply is from N to P. Let's take both of these one by one and see what the story is. And once again, we'll focus on the depletion layer here. This we have discussed in the previous section, that on the P region we have the negative charge which is bound, and on the N region we have the positive charge, and there is a potential difference between the two which we call as the barrier potential. Notice one thing, that the negative charge is on the P side and you are connecting it to the external supply, say of voltage V. By having this positive potential connected to this region which is having negative charge, and the negative connected to the region where we have the positive charge, the effective barrier potential decreases, because it's the other way around. Look at this, negative connected to positive side and positive connected to the negative side. This decreases the effective barrier potential, or you can say even this thickness of the depletion layer is reduced. the decrease of this potential helps the majority carriers from the P region, which are basically the holes. I am showing the hole with these squares. They are pushed on this side, and similarly the electron from the N region are pushed on this side. These majority carriers, they are large in number and barrier potential is less. So movement of the holes in this direction or electrons in this direction develops a forward current I from P region to N region. Since this device is not a ohmic device, so variation of the current with the increase of the voltage is not linear. If we show taking the current on the y side, y-axis, and voltage on the x-axis, we notice two important things. First, the current does not start as we start increasing the voltage. It starts when the voltage becomes sufficiently high, and then onwards we have the current going in a exponential manner like this. However, at large voltages it becomes almost straight. Look at this portion, the last portion. This portion is almost a straight line portion. So if one extend this straight line portion, we reach to a voltage which is known as the knee voltage, Vk. This is knee voltage. This is of the order of a fractional volt. For a silicon, this is 0.7 volt. For germanium, it is 0.2 volt. For this region, the variation is not linear. If I come to the reverse biasing side, the negative is connected to this N region, or this negative region of the depletion layer, and positive potential is connected to the positive charge region on N side. This helps in increasing the barrier potential, and this time the barrier potential becomes VB plus V. As a result, the depletion layer also increases, as well as the barrier potential also increases. Due to the reverse biasing, now the majority carriers have no role. It is only the minority carriers which produces a very small amount of current. One should not forget that in P region we have few electrons which are free electrons, and these electrons are the minority carriers. Due to this negative potential, they are pushed to this side, and same in the N region, the holes are pushed in the reverse side. There is a large potential difference, or barrier potential is large, so even these minority carriers are not easily allowed to cross. Though there is a current which is now in this direction, we call this as a reverse current. But since the number of minority carrier is quite small, so this current is not very large. We show it in the fourth quadrant, taking the current on Y side and the voltage on the X axis. The current is very small and soon it saturates. This is called I0, the reverse saturation current. Let me quickly revise that how the diode behaves. In forward biasing, there are two changes which you should note. Once the barrier potential becomes smaller, depletion layer reduces, and the majority carriers are responsible for the current now through the diode. The current increases with the voltage, initially in a non-linear manner, and soon it takes the linear variation. It appears as if this linear portion starts from a voltage which is known as a knee voltage, or sometimes is called the saturation voltage. This voltage is of the order of, say, fraction of a volt, 0.7 volts in case of a silicon. In reverse biasing, due to the arrangement of the potential, the barrier potential becomes large. Now only the minority carriers are responsible for the current through the diode. Since they are small in number, moreover there is a large potential barrier, so you will find the current is very small. If I compare the two currents, normal diodes have a current in the microampere in reverse biasing and milliampere in the forward biasing. Let's plot these two together to understand some of the characteristics of the diode. If I plot it on one graph, current on the y-axis, voltage on the x-axis, this fourth quadrant corresponds to the reverse biasing and first quadrant to the forward biasing, we can say yes, the current varies like this. And in the reverse biasing, the current is very small and soon it saturates, and we call this current as a saturation current. A formula which represents this type of variation is something like this. This is the reverse saturation current, an exponential function with the power E the electronic charge, V the potential which you are supplying. Eta is a factor, and this factor is nearly equals to 2 for silicon and is equal to 1 for germanium. This is called the ideality factor, which is a property of the material. Kb is the Boltzmann constant and T is the absolute temperature. In the reverse biasing, this factor is almost negligible because the voltage becomes negative. So we ignore this and we have only the reverse current nearly, which is equals to I0. In the forward biasing, this term is large, so sometimes we ignore it and say that initially it is going in an exponential manner because of this. This is known as the diode current or diode equation. I am repeating it, it's important to remember. I is the current, I0 is the reverse saturation current, I0. Exponential function, the charge on the electron, the potential difference which you provide V. Eta is the ideality factor, which is the property of the material. It is 2 for silicon and 1 for germanium. Kb is the Boltzmann constant and T is the absolute temperature. One can out from this region, which is a straight line region, a parameter, say delta V divided by delta. Students, now we are going to learn the diode characteristics. To draw these characteristics, we have to make a circuit taking a diode we have to connect it to a power supply where we can change the voltage. This arrow means that we have an arrangement where we can change the voltage as well as the polarity. We need a voltmeter across the diode to read the potential difference. We need a milliammeter or microammeter to read the current, and there is a series resistance required in order to handle the current so that the diode is not damaged. In this arrangement, the diode is in the forward biasing. The current is going from P to N through the emitter, resistor, and back to this negative. And if we plot the current versus voltage, we get a curve like this. In the next case, when we change the biasing, that means I have to connect the battery as negative to P and positive to N. The voltmeter will have negative terminal here, positive here, and this time the current is going from this positive terminal to the diode. But this is mainly governed by the molarity carrier as I discussed with you, and when we draw it, we get a curve of this type. We have a very small amount of current. In the reverse biasing, which as I told you is of the order of microampere, and from this graph we can read one parameter by reading the slope in the forward biasing. This is delta I and this is delta V. If I take this ratio delta V by delta I, we call this as R dynamical. It is the order of few 100 volt, 100 ohm in the forward biasing, and of the order of a mega ohm in the reverse biasing. In a nutshell, we can say diode acts like a wall which permit the current to go in one direction but almost do not allow the current to go in the opposite direction. That means in reverse biasing it doesn't allow the current. As the current is very small, we can ignore this current. But in the forward biasing it permits the current to go. Based on this, we have one application which we'll discuss in the next lecture. That is the application of the diode. There are many applications like rectification. There are certain diodes which are very special diodes like photodiode, solar cells, Zener diode. They have various type of application. But the main feature will remain that in the reverse biasing the current is very small and in the forward biasing the current is sufficiently good, and we can say it conducts. Thank you.